Alright y'all, today we are talking about combining functions again for the second time. This time we're going to talk specifically about division and something called composition. So we have all of our definitions from last time, right? We've talked about addition, subtraction, and multiplication with functions. Today we're going to start out by talking about division. The definition of this is going to be very similar to our other definitions. So given two functions, that's supposed to say functions, f and g, the quotient function f over g is defined by f over g of x equals f of x over g of x for g of x not equal to 0. Why would we want g of x to not be 0? Well, where is g of x? It's in the denominator, right? Denominator and 0 doesn't mix, right? We don't want our denominator to be equal to 0. So, because of that, g of x cannot be 0. So this is saying it's not defined. The function f over g of x is not defined when g of x is equal to 0. Let's look at an example of this, and in that example we'll also sort of refresh on how to add, subtract, and multiply. So let h of x equal x squared minus 1 and j of x be the square root of x minus 2. Okay, so first let's kind of just go down the list. Let's find h plus j of x. Remember, all we're doing is just adding the two functions together, right? Our formula was h plus j of x is equal to h of x plus j of x. And then we replace each with what they're equal to. So h of x is x squared minus 1. J of x is the square root of x minus 2. Can we simplify here at all? We can't, right? We can't simplify here. So, right, we have a squared term, we have a constant term, and we have a square root term. So this is as simplified as it's going to get. We can't combine any of these guys. So this is done. H minus j of x is similarly h of x minus j of x. And again, we replace those guys. With subtraction in particular, it's important that we make sure that we're subtracting every term. So sometimes it's nice to have parentheses, right? We could have parentheses around all of these if we wanted to. Again, we're as simplified as we can get, so this is done. H times j of x is h of x times j of x. We replace them. This one we definitely need parentheses, right? We want to make sure that we know to multiply all of these terms by this guy. We can simplify a little bit here. If this had asked us to simplify, we can simplify. There's a couple of things we could do. So we would want to simplify by distributing, right? We want to multiply this guy by both this term and this term. So we would end up with x squared times the square root of x minus 2 minus 1 times the square root of x minus 2, or just the square root of x minus 2. So that's this simplified. I know it doesn't look super simple, but it's just a messy answer. That's okay. All right, last one. Let's say we were asked for h over j of x. This is our first quotient function. This is our first division. Again, above, it's just h of x over j of x. Here, h of x is x squared minus 1. J of x is the square root of x minus 2. Simple as that. There's nothing we can really do here to make this more simple, so we can leave it as is. Okay, so we talked about the domain of all of these guys, right? We talked about the domain for addition, subtraction, and multiplication, right? And we said that the domain was what's in both, right? The intersection of the domains of f and g. Is there anything that's going to be different for the quotient function? Well, we're defined by f and g, right? So again, we're going to need to take into account what the domains of f and g are. But we also have this additional condition that g of x is not 0. So domain of f over g of x is what's in both the domain of f and the domain of g, excluding where g of x equals 0. Example, what's the domain of the function above? Well, the domain of h was x squared minus 1. That doesn't have a denominator, doesn't have a square root, so that is all real numbers. What's the domain of g? Well, g was the square root of x minus 2, which means that we need to set what's underneath the square root greater than or equal to 0. We end up getting x is greater than or equal to 2. So we found what's in the domain of our top function, what's in the domain of the bottom function. Now we need to figure out where the denominator function is equal to 0. So where is the square root of x minus 2 equal to 0? Well, we know the square root of x minus 2 is going to equal 0 when x minus 2 is 0, right? So that means that when x is 2, then g of x is equal to 0, or j of x here in this case is equal to 0. So x cannot be 2. We want to exclude where x is equal to 2. So we need our domain to satisfy the conditions that x needs to be greater than or equal to 2, but also not equal to 2, right? Don't want to be equal to 2. And then all real numbers doesn't change anything, so our domain is 2 to infinity. Now, something I would like for us to look at is if I just looked at this function on its own, if I just looked at x squared minus 1 over the square root of x minus 2, the domain of this function would also just be 2 to infinity, right? On its own, if I just looked at this. The domain of this function is 2 to infinity, right? Not including 2. Because we would know, okay, I have a square root, so I need to make sure that whatever's underneath is not negative. And I also know that I have a denominator, so this can't be equal to 0. So we would have gone through the same process if we were just looking for the domain of this. And that is a trick we're going to use for combining functions. The domain can be found by using domain rules before simplifying. So, for example, let's look at a couple of questions. Let's say we have f of x equals the square root of x minus 3, and g of x is x minus 5. F over g of x, what is this? Well, f of x over g of x. We just write f of x on top, and we write g of x underneath. What is the domain of this function? Well, it's the domain of our combined function without simplifying, right? So we use our domain rules before simplifying. So our domain rules say we need to take what's underneath the even root and set it greater than or equal to 0. So we end up with x needs to be greater than or equal to 3. Our domain rules also say that we can't have a 0 in the denominator, so we need to figure out where the denominator is equal to 0. We solve for x, we get that x cannot be 5. So we want x to be greater than or equal to 3, but not equal to 5. So we have an open point on 5. We can be equal to 3, so we shade everything that's greater than 3 except for 5. And that will give us the domain 3 to 5, not including 5, and then 5 to infinity. That is the domain for this function. We wanted to use our domain rules before we simplified. This is already as simple as it's going to get. Let's see where it comes in handy for us to use our domain rules before simplifying. So let's say I asked y'all for g over g of x. That's totally fine. We're totally allowed to do that. Remember, these are just names of functions. I'm allowed to pick the same function for the top and the bottom. That's totally fine. So what is this? Well, our definition just says that it's g of x over g of x, which means I have x minus 5 over x minus 5. In order to find the domain here, we need to use our domain rules before simplifying. So that means I have a denominator of x minus 5. I need to set that not equal to 0. That tells me that x cannot be 5. That's our only rule, so we can go ahead and write that in interval notation. We want it to be all real numbers without 5, so we take out 5. That's my domain. Okay, now that we've found our domain, we can simplify something over itself. What does that equal to? It's the same thing as 2 over 2 or 6 over 6. It's just 1. But it's not just a regular old 1, right? For every x value, the y value of this function, the output of this function is 1 for every x value except for 5. At 5, it's undefined. Let's look at the lab manual just for a couple examples here. This is the section Operations with Functions and Compositions of Functions, Symbolic and Algebraic. So our first problem, problem 1, so we have our two functions here. It's asking us for f of x over g of x. This is 5x plus 4 over x squared minus 1. We can't really simplify that at all, so we're done. What is the domain of this function? Well, we can look at the function itself and find the domain because we didn't change it after, we haven't simplified, we haven't changed it at all by simplifying. So what is the domain of this function? Well, it looks like it's all real numbers because the numerator has no even roots. Our denominator, we need to figure out where it's equal to 0. We can do this in one of two ways. We can either factor. This factors into x minus 1 and x plus 1. This is the difference of squares. Then we split them up and solve. The alternative way to solve that would be to bring the 1 over and then take the square root of both sides, which would mean that x would be plus or minus 1. So both gave us plus or minus 1. We don't want x to be plus or minus 1, so our domain is all real numbers. We take out negative 1. We also take out positive 1, and then continue to infinity. All right, problem 2. F of x is square root of 5 minus x. G of x is square root of x plus 1. So we have a square root in the numerator, which means that we need whatever's underneath to be greater than or equal to 0. We have negative x is greater than or equal to negative 5. We divide by negative 1, but when we do that, we have to flip the sign. So we have x is less than 5. We also know that we have a square root in the denominator, which means that what's underneath needs to be greater than or equal to 0 because it's a square root. But we also know that because we're in the denominator, it can't be equal to 0. So we want what's underneath to be just greater than 0. This one's a lot simpler to solve for. We just get that x is greater than negative 1. Let's put this one on a number line just to see exactly what's going on. So we have negative 1 and 5. We want to be greater than negative 1 and less than or equal to 5. So we have a open point on negative 1, shaded point on 5. And that means the points that satisfy both are going to be what's in between. So our answer is parentheses negative 1 to 5 bracket. Okay, so that is division of functions. Let's talk about composition. I'm going to start off with just a quick definition. When the output of a function is the input for a second function, the two functions are said to be composed. So what does this mean? So we have a function. Let's look at our kind of machine visualization that we've been looking at this semester. So we put x into some function g and we get out g of x. This is saying that that output is going to be the input for a second function. So this output is going to be the input for a second function, let's call it f. When we put x into g, we pull the lever, then we take g of x and put it into f and pull the lever. We get f of, normally we would have f of x because we put in x, but this time we put in g of x, so we are going to have f of g of x. We're going to give this function a name, as we do with all functions. The name of this function, that's going to take us straight from x to this answer, where we get f of g of x, is f of g. That's a little circle, little open dot. So this function is f of g of x, and it's equal to f of g of x. Formally, the way we say this is g composed with f of x, but that's confusing because it's backwards and it's also just a mouthful. So more often, you'll just hear people say f of g of x. And that's nice for two reasons. It's nice because it kind of tells us exactly what's going on here, right? It says that this is equal to f of g of x. It's also nice, in my opinion, when I was learning this, I would always think of this open dot as a tiny o. So f, and then o for of g of x. If that helps, great. If it doesn't, don't worry about it. That is what we call this. That's what we're going to call it in this class. So let's give this a shot. Example. Let's say we have f of x equals x squared and g of x equals x plus 1. First, let's look at f of g of 2. Before we look at the general x. Our formula says, or our definition says, that this is equal to f of g of 2. Well, what do we do here? We replace less useful things with more useful things. What is g of 2? Well, we can figure it out, right? G of 2 means we've replaced x on this side with 2, so we replace x on this side with 2. So we get 2 plus 1, or 3. 3 is the output of g at 2. So we replace g of 2 with 3. Now it's asking us for f of 3. We've replaced x with 3, so we replace x here with 3, so we get 3 squared, which is 9. So the answer here is 9. We could do the same thing backwards. Let's see if it gives us the same thing. G of f of 2. Our definition says this looks like g of f of 2. We want to replace our inside. F of 2 gives us what? Well, we replace x with 2. we get 2 squared, which is 4. So we have g of 4. What is g of 4? Well, again, we replace x with 4. So we get 4 plus 1, which is 5. So our answer here is 5. These are not the same. Composing these guys backwards, right, flipping the order, does not necessarily give us the same answer. So we want to keep that in mind. What if I asked you to compose f with f? Let's check it out. We've got f of 2. If you're having a hard time writing this from this, then I would encourage you to kind of say it to yourself, sort of say it out loud. F of 2, right? F of 2. What is f of 2? Well, f of 2, again, we already said was 4. So we have f of 4. F of 4 is just 4 squared, which gives us 16, right? So 16 is my answer. That's it. Simple as that. You could do this with graphs, right? By pulling the output values from the graph, right? We would just look at the graph and see, oh, what's f of 2? And then you would see, oh, f of 2 is 4. And then you would look at the graph and see, where is f4? What's the output of f at 4? And you would see that it was 16. That's how we would do it with a graph. Very simple. Okay. Now, on to the big leagues. Let's say we're asked for f of g of x. Well, our definition says that this is just f of g of x. We again want to replace things with more useful things. What do we know about g of x? Well, g of x is equal to x plus 1, right? So we can replace g of x with x plus 1, right? These are equivalent. I'm putting kind of this little underlined thing on both of them because they're the same. Now, what is f of x plus 1? This is interesting because it's not a single number, right? So what are we going to do here? Well, we know that if I had asked you to find f of 2, right? We did that a couple of times. We know that because f of x is x squared, then f of 2 is just 2 squared, right? F of 4 is just 4 squared. F of, for instance, smiley face is smiley face squared, right? That doesn't really mean much, but we just replace x with whatever's inside. So if f is x plus 1, then we replace x with x plus 1. That's all we're doing here. So we have x plus 1 squared. We want to think about this as, okay, I'm putting something, right? Maybe it's a black box into f. And f is taking whatever that is and squaring it. So if I try to plug in x plus 1 into f, I'm going to get x plus 1 squared. So here we have x plus 1 squared. If it didn't ask us to simplify, this would be the answer. If it did ask us to simplify, we would need to simplify. How would we simplify this? Well, we would need to FOIL, right? X plus 1 squared is x plus 1 times x plus 1. This is going to give us, first terms multiplied together is x squared. Outside terms are x, inside terms are x, so we end up with 2x. And then last terms are 1. This is the answer simplified. Let's look at g of f of x. Again, our definition says g of f of x. We want to replace f of x with what it's equal to. We know that f of x is x squared. So g of x squared is, well, so because g of x is x plus 1, it means we're taking whatever we put in and adding 1 to it. So here we've put in x squared, so we're going to get out x squared plus 1. This is as simple as it's going to get, so this is our answer. Let's look at f of x equals the square root of x plus 2. And let's say h of x is x minus 5. What is f of h of x? Well, our definition says f of h of x looks like this, f of h of x. Let's replace h of x with what it's actually equal to, so we end up with f of x minus 5. When we plug x minus 5 into f of x, we're going to end up with square root of, remember we're replacing x in both places with x minus 5. So here we're replacing x with x minus 5. X minus 5, I like to use parentheses, plus 2. This is the answer unsimplified. Let's find the domain. Speaking of simplification, remember our domain from before. We can find the domain of a combination of functions by using our domain rules before we simplify. What domain rule are we going to have to use here? The one where we have even roots, right? Even roots, we need to take whatever's underneath and set it greater than or equal to 0. So here we have x minus 5 plus 2 is greater than or equal to 0. We can take the parentheses away. We have x minus 5 plus 2 greater than or equal to 0. We can combine like terms. So we get x minus 3 is greater than or equal to 0, which tells us that x needs to be greater than or equal to 3. So our domain is 3 to infinity. Maybe it doesn't super make sense why we needed to do this before simplifying, but I'll show y'all an example pretty soon of when we would need to do it before simplifying. Now that we've done that, let's go ahead and simplify. Again, when we take away these parentheses, we can combine like terms. So we have minus 5 plus 2, which leaves us with x minus 3. So that is f of h of x. An example of why it's important for us to do this before we simplify, the same function f, but let's make our second function, g, a little bit more interesting. So let's say g is x squared plus 1. And let's say that I've asked for g of f. Well, what is g of f of x? Well, it's g of f of x. F of x is the square root of x plus 2. I'm plugging the square root of x plus 2 in for x here, so we replace both x's with the square root of x plus 2. So we have square root of x plus 2 squared plus 1. So in order to find domain, we don't want to simplify it all from here yet, but we do need to use our domain rules. Our domain rules say that we need to take this x plus 2 and set it greater than or equal to 0. We solve this. We can subtract 2 from both sides. We end up with x is greater than or equal to -2. So my domain is -2 to infinity, which is pretty clear to see here, right? Anything less than -2 is going to give us a negative under the square root. But when we simplify, let's say this told us to simplify, what happens when I square a square root? They sort of cancel each other out, right? Squaring a square root gives us whatever's underneath. So we end up with just x plus 2 plus 1, right? And because these parentheses don't really do too much with just addition, we can combine these like terms, and we end up with x plus 3. So technically, this function simplifies to x plus 3, but because we got it by doing all of this craziness, we still can't have anything less than -2. So even though this turned out to be a very simple function, it actually has some weird stuff going on underneath. So we need to make sure our domain reflects that. Let's say we were looking at f of x equals 3 over x, and g of x equals 3x plus 9. Let's find f of g and its domain, g of f and its domain, and f of f and its domain. Okay, f of g just looks like this. G of x is 3x plus 9. We plug that in for x in f. We end up with 3 over 3x plus 9. What is our domain here? Well, we don't want our denominator to be 0. So we set 3x plus 9 not equal to 0. We end up with 3x does not equal -9. So x does not equal -3. That means our domain is -infinity to -3, not including -3, and then all the way to positive infinity. What is g of f of x? G of f of x. Well, f of x is 3 over x. We want to plug 3 over x into g of x here, so we have 3 times 3 over x plus 9. We want to use our domain rules before simplifying. So our domain rules, we just need to look out for denominators and even roots. We don't have any even roots, but we do have a denominator. And that denominator is simply x. So if we set our denominator not equal to 0, it just tells us that x can't be 0, right? Makes sense? So our domain is just -infinity to 0, and then 0 to infinity. if we were told to simplify this, we would need to multiply these terms together. So in order to multiply, this is 3 over 1. When we multiply numerator by numerator and denominator times denominator. So we have 3 over 1 times 3 over x, so we end up with 9 over x plus 9. That is the answer. All right, f of x. F of x is 3 over x. So then f of 3 over x is going to be 3 over 3 over x. Super weird. So we want to use our domain rules with this. So wherever we have a denominator, we don't want that denominator to be 0. So I see two denominators, right? I see this denominator here, and then I see this guy as a denominator also. So x is a denominator, so we don't want x to be 0, and we also don't want 3 over x to be 0, right? So we know that x can't be 0. We want to take x out of our domain. This guy we want to think about a little bit. When is 3 over x going to be 0? When is any fraction 0? A fraction is 0 when its numerator is 0, right? 0 over 1 or 0 over 3 or 0 over 12 or whatever. So this will be 0 when the top is 0. The top is 3. Is 3 ever going to be 0? No, 3 is not 0, so it's never going to be 0. 3 is 3. So 3 can't be 0. Well, that's true, right? That doesn't tell us anything special. So that's all good. We don't have to do anything different. We do need to still make sure that x is not 0. So our domain is negative infinity to 0 and 0 to infinity. All right, 3 over x. How can we simplify this? Kind of ugly. Get a fraction out of a fraction. How do we simplify this? Well, if I have 1 over 1/2. Again, remember, fraction is just asking us how many times does this fit into this? How many times does 1/2 fit into 1? Twice, right? So 1 divided by 1/2 is 2. The way we can change this or see this more clearly is division is the same thing as multiplying by the reciprocal. So 1 divided by 1/2, the reciprocal of 1/2 is 2 over 1, right? Reciprocal just means we flip. And that gives us 2. The clearer way to see this is translating 2 over 3. 2 over 3 is the same thing as multiplying 2 by 1/3, right? So that's why 1 over 1/2 is the same thing as 1 over 2 over 1. 1 times 2 over 1. So here we're trying to divide 3 by 3 over x. We end up with 3 times the reciprocal is x over 3. So we get 3x over 3. We have one term with 3 over one term with 3, so these guys cancel and we end up with x. Okay, so now that we've talked a bunch about composition, let's talk a little bit about decomposition. So if composition is what we've been working on, then decomposition is kind of just working backwards. So decomposition is asking us to find two functions, f and g, that would give some function f, which is f of g. And in this last portion, we've been taking two functions and composing them together, right? Putting one function kind of inside of the other function. Now, what we're going to be asked to do is take a function where that has happened, where we have put one function inside of another function, and sort of take them apart. So, for example, let's say you've been given f of g, or big F, or whatever, equals 1 over x plus 3. So in my opinion, the best place to start with these types of questions is figuring out what is the inside, right? What is the inside function here? What is our g of x? What is on the inside? Kind of working from the x outwards. So I like to rewrite it. I like to write f of g of x, or whatever the terms are that we're using. Rewriting it like this. And saying, okay, I'm going to box off g of x. I'm going to box off my inside function. I'm using the color red for that now. So what over here looks like it could be my inside function, right? We want to start with x and work outwards. What is inside here? Well, a good place to start would be this x plus 3, right? If x plus 3 is my inside function, then what have I done? If I sort of carry this over, again, sort of like what we were thinking about earlier, we can just sort of think about this as like a box, right? So we're taking f of box, and we've also taken the x plus 3 out, so we have what's left is 1 over this box, right? Red box. And all we need to do is just call that box x. At the end of the day, that's the point of variables, just kind of standing in place of some other stuff, right? So f of x is 1 over x, and g of x, right? We said we're making these equal. G of x is x over 3, or x plus 3. We can check by combining them, right? If I take f of g of x, and g of x is x plus 3, then I've got f of x plus 3. And if I'm putting x plus 3 into 1 over x, then I'm replacing x with x plus 3. So I have 1 over x plus 3. That's what we started with. So we are good. So our answer is kind of both of these. So I have to do kind of a crazy square. Let's look at another one. Let's say we had f of g of x equals square root of x squared plus 2. So let's rewrite again. So we've got f of g of x equals this stuff. So we want to close off our inside function and pick whatever we want it to be equal to over here. So I'm going to go ahead and pick all this stuff underneath the square root. Right? That's a great choice for an inside function. That would mean, so that would make g of x, we've set that equal to x squared plus 2. And that would make f of x, right? Again, we have f of square, so f of x is equal to the square root of square, right? Red square. So the square root of x. And this is my answer. This isn't the only way I could have done this, though. If I wanted to, let's write it again. I'll use a different color this time. So this time, I'm going to make my inside function the purple square. My only requirement for an inside function is that I need to work my way outward. So I start at x and work my way outward. So x squared also works. X squared is a perfectly good inside function. So here, if g of x is x squared, then what's left over? Well, f of purple square, which is, we're going to call x, is equal to the square root of purple square plus 2. So our function is f of x equals the square root of x plus 2. These are both correct. You only need to give one. One thing that I do want to mention with these decomposition questions is that when you see the instructions written out, it might say, give a non-trivial answer. A trivial answer would basically just be to say, all right, I have the function x squared plus 2, or sorry, square root of x squared plus 2. So I'm going to split that up into f of x, and I'm going to let f of x be just x, and g of x be the whole rest of the function. That's a trivial solution. When we compose these guys, you do end up with the right composition, but it's not telling us anything interesting, right? So that's all it means by trivial. Let's look at a few practice problems from the lab manual. Again, this is from the section Operations with Functions and Compositions of Functions, symbolic/algebraic. So looking at this first guy. So again, we are given big F. We want to split it up into a small f and g so that when we compose them, it gives us big F. So let's write this down like we have been. So how can we split this up? Well, so again, there are multiple answers here that are correct. What are they? Let's start by the smallest g function. Again, when you do this, you only have to find one. You don't have to find all of them, but I want to give all the correct answers so that folks know if they're doing things correctly. So the smallest g of x could be is x squared, right? That's the closest to x. If we let g of x be x squared, then f of x is everything else, right? So f of x is the 1 and the plus, and the x squared would go here, but we've blocked it off, right? So that's just x now, cubed. And that's our answer. That's one correct answer. If that feels confusing, take a second and pause and do the squaring off, right? Take a color, or maybe not a color, take your pencil and box off what you want to be the inside function to help you find this answer. Okay, so that's the smallest g of x we could have chosen. Let's take one step out. So the next step here, we have x squared. We definitely need to choose something that has x. Well, okay. Yeah, so we chose x squared. Now let's take up x squared plus 1. So let's let g of x be x squared plus 1. That's also a possibility. If g of x is x squared plus 1, then we want to replace all of that with x for f of x. So if we replace all of that with x, then we just have x cubed. These are the two solutions for that. Let's look at number 2. Again, we can rewrite it. Let's choose our inside guy first. Again, I'll start with the smallest one, right? And we'll work our way out. So starting with the smallest g of x, we can't just choose x because that would be a trivial solution. So let's choose 2x. If we choose 2x for our inside function, then the rest of f of x, right, this has been boxed off. So we have the square root of box, or x, minus 9. So square root of x minus 9. That's one solution. Another good solution, let's take one step out. So we can't choose x, but we chose 2x. So let's get a little bit bigger, and we have 2x minus 9. That means that leaves us with an f of x of the square root of, we box that off, so all of that becomes our x, so f of x is just the square root of x. That is our second possible solution. Either of these would be correct, you just have to give one. All right, why don't you guys try 3 and 4 here. Pause the video, and I'll talk a little bit about them afterwards. Okay, so this is what I got. This first one, we have 2 possible solutions again, right? We can't choose x for g because that would be a trivial solution. So our first step outwards from x is 2x, right? So if we let g be 2x, then we end up with f, this f here. Our next step outwards after 2x would be 2x plus 7. So that's where g is here, and that would mean our entire denominator becomes x for f. This guy actually has 3 possible solutions. Again, we can't just let it be x, that's trivial, but our next step out from there is x squared. We end up with this f in that case. Our next step out from there would be 2x squared. That leaves us with this f. And then our next step out would be to let the entire inside of those absolute values be our g of x, and then let f of x be just the absolute value. Okay, that's it for decomposition, and that's it for combining functions. I know this was a long lesson. Thanks for sticking with it, and thanks for watching.